Kyushu University. And he is a very well-known polymer chemist in chemist, and he is now a professor of the Department of Macromolecular Science and Engineer at Kyushu University in Cleveland, Ohio. So he is well-known and published many nice scientific papers, and he is a fellow of the American Chemical Society and a fellow of the Polymer Science and Engineering Division, ACS, and also a fellow of the Polymer Chemistry Division. There are two different divisions, Polymer Division, and also he received the Distinguished Mark Scholar Award, and also elected to the World Economic Forum Future Materials Research Council in 2016. And he served as the first chair of the Polymer Division, American Chemical Society, and he is the editor of the active and functional polymers, and recently recent associate editor of Polymer Science, and he is now the editor-in-chief of the material MRS communication. And his group doing many fields of the polymer research, including polymer synthesis, particularly polymer brushes, and also nanomaterials, and also 3D printing and thin films cover application from smart coatings to biomedical devices. So this time he is visiting Lotus University, and for almost 2 months. And I asked him to come to Kyushu University, and he kindly accepted our invitation. And today he gave a talk on non-structured and templated polymer materials and the interface. So let's welcome Professor Tsuno.
Thank you very much, Takara-sensei, for that generous introduction. And of course, it was nice to see you again here and meet your group and new colleagues. Secondly, of course, I'd like to thank the center, the institute, the I²CNER, for this opportunity to give the lecture, also on behalf of the institute. And it's surprising that we get to know a lot of other people we know and how things are connected. So pretty much, this is my first time to visit Kyushu University, Fukuoka. It's a very different feeling because every time I visit Japan, I always only think of visiting Tokyo. But now I have a new favorite place to visit. Maybe in a cooler time, not as hot as today. But and then lastly, I appreciate you for coming here. I know it's a hot day outside, and you know, some of you came from other buildings, perspiring, huffing, puffing, just to get here. So thank you so much for being here. So I would like to talk to you today about nanostructured and templated materials and interfaces. Actually, my message, basically, especially for the young researchers, is that the pathway from basic platforms in science that you get to learn from your research at the university is not too far from what we call innovation. Innovation is essentially translational research or applied research that becomes very important and maybe even cost-effective to the marketplace. Now, I have been doing research, or as an independent researcher, for 20 years. I did not imagine many of the things that I do might eventually be useful or skills of interest to the industry. But today, let me concentrate on different sets or skill sets of materials, namely nanostructured materials and interfaces. So with that, is it possible to dim the lights in this side? All right. So if the is the volume correct? Loud enough at the back? Can you hear me well? Good. Daijoubu. So from Kyushu University, we are in Cleveland, Ohio. Ohio gozaimasu. In Ohio, here in Cleveland, in a not so different weather, but usually in summer we can only get as hot as about 22, 25 degrees Celsius. Very nice. And this is really a nice summer day in Cleveland, Ohio. But during winter, everything is covered with snow, white, okay? And quite cold. So my building, and Takahara Sensei has visited us already, gave a lecture as well. Our building is located here at the Macromolecular Science Engineering building. And this is the rest of the campus. We have the medical school. We have Cleveland Clinic over here. This is my favorite part of the university because here is the home of Cleveland Orchestra. Okay, quite famous orchestra in the United States. Also, here is the home of the Cleveland Museum of Art, a highly endowed institution where we have a collection of impressionist art, ancient art, Manet, Monet, different types of modern art, and it's free. You can just go in there and you don't have to pay anything. The collection here is comparable to what you'll find in the Metropolitan Museum and also in Chicago. Okay, so in one of the sunny days or winter days, you'll find YJ walking in this area. YJ Lee is staying in the Takahara group. His stand-up YJ. And he actually works in my lab as well. So, everything here is familiar. But I don't know, YJ, if you know some of these facts. So, for example, of course, in the Cleveland Museum of Art, there's a lot of culture. You can also go to the lake. So we have some lake sports during summer and some fish, maybe mostly trout. Also, if you like orchestra, as I said, the Cleveland Orchestra is here. But there are several things you ought to know about I²CNER University. So, for example, how many of you have seen the movie Air Force One? Have you seen this movie? Okay. For those of you who have not seen this movie, you can Google or watch YouTube. Okay, after my talk, not during my talk. Air Force One, the opening scene, where you have paratroopers or security forces coming in at 9. That was actually shot here, right here. Okay, so watch the movie and you'll see that building. Okay, how many of you have seen the movie Captain America, Winter Soldier? Okay, again, you can watch YouTube later. Okay, Captain America, Winter Soldier, the headquarters of S.H.I.E.L.D. One of the scenes in the middle of the movie was actually taken here at the Cleveland Museum of Art. So otherwise, I²CNER University is known as the Hollywood of Ohio. Okay, just kidding. It's not official, but this is how I look at it. So this is my department. This is my office. This is our lab. We have another lab on the 3rd floor. These are some of the graduate students, masters and PhD students work in my lab. They need to do a new one. But basically, we are a lab very similar in many ways to Takahara Sensei in focusing on interfaces, surfaces, polymers and chemistry, reactive chemistry as well, and using very good surface analytical methods at the interface. So we do a lot of work, let's say, responsible for patterning or spectroscopy at interfaces or utilization of new telecalic materials or molecular imprinting, also looking at different types of dendrimer structures, patterning, and different types of colloidal templating. In fact, a lot of these things here, if I look at this cover page of papers, I don't remember the work per se, but I remember the face of the students who worked for me or who got all those papers. Actually, Tamada Sensei, we actually had some collaborations in the past where she had sent some students in my lab. So the interaction on interfaces and this type of chemistry, I'm very familiar and is very familiar here at Kyushu University. Another phase on my group, which I of course don't advertise, is collaboration with industry. So some of the projects I've done in industry range from, of course, consulting work, but also long-term projects, even with some Japanese company. But it just underlies the importance of interfaces or thin films that are also commercially translatable. Or the favorite part I have is looking at industry-related projects and seeing how I can apply the best platform you can get from your research in applied research. So in a way, we try to bridge the gap between what we do in the university and what is the marketplace. Okay, and I'm not alone, or this type of work is done for every professor. But it's just that in the type of things we do, we also try to relate it to industry. It's all about cost and performance ratio. So let's start moving forward towards the bulk of the talk. When we talk about polymers in general, we also look at the interfacial phenomena, not just the bulk property, because what happens at the molecular to nanoscopic level eventually becomes a macroscopic property. And as you can see here, a polymer can be disposed as or predisposed as a film or as a particle. A polymer that is ordered at the film starts from the nanostructure level, the layer by level, and then the continuous or bicontinuous level as membranes. On the other hand, a polymer can be used as a micellar, vesicular, or emulsion type of ordering, even Pickering emulsions that make it responsible for controlling fluid or thermoresponsive or stimuli-responsive behavior, such that I can claim, or a lot of you can claim, that polymers are true nanomaterials. Okay? Maybe not to the same extent that we look at quantum dots or gold nanoparticles or carbon nanotubes. But by the extent of chemistry and ordering you can derive from a polymer, it is the most versatile nanomaterial. Now here you can see a collage of different types of interfacial phenomena that can be translated to layer order. So of course, you're familiar with chemical adsorption, physical adsorption, Lambert-Blodgett film deposition. Not too well reported are of course things done under chemical or vapor deposition methods, or even electropolymerization techniques. And of course, well known is polymer grafting or polymer brushes. So today I am going to tell you the breadth and length of the things we do at this scale. But before you do that, let me emphasize the importance of synthesis. So chemical synthesis, or the ability to make new polymers or oligomers, is the key towards getting a range of properties that allow you to control things at that level. Whether it's amphiphilic or energy transfer or different types of hierarchical structure starts from synthesis. And so we have done, for example, many things related to dendrimeric structures or organic electronics by playing with the homo-lumo level of various charge transfer and energy transfer systems. On the other hand, we like to play around with dendrimers. So dendrimers for us are what we call shell or coating of particles, where we can use a hyperbranch approach to populate a high density of reactive groups or N groups that are useful for ordering, and stacking. So we have done a lot of work related to what we call hybrid nanoparticle dendrimers. In another aspect, and this is more recent of the work we do, we like to use supramolecular templating, where we take various types of supramolecular structures and then grow the ring towards what we call catenated and knotted polymer systems. As some of you may recall or like the work in supramolecular chemistry, that means the ability to control the orientation or donor-acceptor or even hydrogen bonding type of interactions to lock in a particular topology, and then in our case we want to grow them such that we have reported, for example, the first type of polycaprolactone trefoil knot through a bidentate ligand design. So this just tells you that everything starts from the molecular to macromolecular level. So today, with the amount of time I have, how much time do I have for the lecture? Akaras, I say?
I think you can talk until 3 o'clock.
Until 3 o'clock.
And then we have a question.
Okay, good, good. I have about 300 slides. I'm just kidding, I'm just waking you up. So I have at least 5 different projects I'd like to cover with that amount of time. Maybe I will not have time to discuss up to the 5th project, but we'll see. But at any rate, this is what I want you to remember. Everybody loves fake news these days. You know fake news, right? You watch television, US television, you know, fake news, fake Russia, fake this and fake that. Today, I want you to look at the fake materials in my talk. Okay, I'm going to talk to you about fake materials today. So let's see how much fake materials do you remember from this talk. So the first talk, let's focus on molecular imprinting. Okay, molecular imprinting towards sensors. Now, with this, you can see that an enzyme, essentially an enzyme could be a catalytic or receptor function, is dependent on the interaction between a substrate or a chemical and a structural biology. In other words, the exact orientation and interaction leads to specific adsorption or specific kinetics. This can be either by a rate model, occupational model, or induced model that results in lowering of that activation energy. Now, what's interesting for me is when I look at an enzyme, and you have different sizes here, this is almost like a generational growth of a dendrimer. In other words, we're talking here about particles or chemical species that range from generation 1 to generation 7 with sizes of sub 1 to about 5 nanometers. Okay? So and that means that the chemistry you can do is within that level. Now, artificial biochemical receptors means that you are looking at specific function by which, let's say if an enzyme doesn't work, it means trouble. That means you cannot live with a healthy living and have some diseases. But actually, it all boils down to what we call lock and key mechanism. What is a lock and key mechanism? Very simple. A lock and key mechanism means I have a key and it can only be used in one lock. Or if I have a master key, at least I can open several locks. That means the interaction between the lock and the key is specific. Now, if I have a key and a lock, that will work. But if I have a key and I do not have the lock, then I have to make the lock. Okay? And that is essentially molecular imprinting. Molecular imprinting is I know the molecule, I know the analyte, but I don't have a lock. I need to surround or build a chemistry that will enable me to do a lock. Now, it sounds so simple, of course, but by design, what you're trying to do is you want to take a chemical, you want to surround it with monomers or cross-linkers that will complex with the analyte, and then you can do cross-linking or polymerization such that you form essentially a cavity. that's very specific for this molecule. And if you do that, you'll end up with a adsorption, desorption kinetics or binding constant that is quite high. That means you build in specificity. So take it in another picture here. This cavity stabilizes that chemical reactant or analyte or peptide such that it can selectively distinguish it from other molecules. Okay? Now, molecular imprinting is not new. It's been around. Everybody has done it. Our twist is we have basically used electrochemistry or electropolymerization to improve on molecular imprinting. So in molecular imprinting, our way, we would create monomers that can complex with the analyte. These monomers are electropolymerizable, meaning we can use cyclic voltammetry to polymerize them into cavities where the molecule can be removed or bound or desorbed or adsorbed on this cavity back and forth, back and forth. So this is essentially a sensor for this molecule. And if we build this sensor on what we call an SPR chip, right, surface plasmon resonance electrode or gold plate, we will end up detecting the binding or rebinding or detection of that analyte by changes in the reflectivity. Now, the gold surface here is just one type of transducer. I can use a quartz crystal microbalance, I can use an optical fiber, I can use a Raman substrate, and I will get different types of magnitudes of effect, but the same thing. I will detect it. Okay? I will characterize the binding constant. Now, what's interesting for us is when we look at this chemistry, essentially an analyte is surrounded by molecules that looks like a dendrimer. So essentially, we're trying to electropolymerize a dendrimer-like complex. So in this case, we have used, let's say, polythiophene that was polymerized here to detect theophylline. And then this cavity is very specific for theophylline. Now, this is caffeine. How many of you drank coffee this morning? Okay, so caffeine looks like this. And then if you look at this molecule, theophylline, theobromine, what do you notice? They almost look the same. The question is, can I build a sensor that distinguishes it from theophylline, theobromine? Paracetamol definitely is different. Naproxen, another different molecule, which are analgesics. In other words, these are drug templates where I want to distinguish a caffeine from the rest by molecular imprinting the caffeine and see if I can get very high sensitivity. So, the monomers we use look like this. These are terthiophene, carbazole, electropolymerization around 6 volts, interaction with the analyte by hydrogen bonding. So we can surround the molecule with these monomers, electropolymerize it by CV or potentiostatic methods, and come out with a very sensitive sensor for the original template. And for example, before we do this complexation, we actually try to model the degree of complexation between the analyte, in this case theophylline, with the number of monomer pairs that will lead to higher binding constant. And we do this by ab initio semi-empirical calculations, or simply MM2 calculation. That shows that for theophylline, for example, we have optimum complexation with 1:2 ratio. Okay? 2 monomers to 1 molecule. So this was done essentially by electropolymerizing this on a gold working electrode. This gold working electrode builds a film that constitutes the template plus the polymer, and then we can remove the template and form cavities on that film. Once we do that, we can use SPR to detect back and forth, or to distinguish the template from other analytes by sensor studies. So the result is as follows. When we templated naproxen, the rest of the molecules did not respond. When we templated theophylline, the rest of the molecules did not respond. Notice that caffeine and theobromine have almost similar structure as theophylline. Shows you how sensitive the film is to the original template. Or paracetamol, the same thing. So this is what we call highly sensitive or selective films, even with a dynamic range that we have found to reach to picomolar level. So most of those details have been published. Now, we can take folic acid. Folic acid has this structure. We can then complex it with this monomer. And we did the study with 1:3 ratio in terms of the complexation, but the same result. We can get very sensitive quartz crystal microvalent sensors for folic acid using the electropolymerization method. And not only that, we have demonstrated it to many others. For example, sarin, dopamine. Sarin, how many of you know what sarin is? Okay, there's been a chemical attack in Tokyo on sarin many years ago. It's a nerve agent that kills within minutes. Okay, actually it's been used recently in Syria. Okay, so we can detect sarin very well. Dopamine, okay, sometimes used in blood clotting. TNT, what's TNT? Explosive, okay. So of course I don't want dead students in my lab, so we had to use DNT, okay, or not sarin, but actually we use another analog. So bisphenol A, okay, melamine, painted milk, okay. How about morphine? How many of you taking drugs right now? Okay, hold on. Morphine, also with aspartame. We have demonstrated it to 5 other molecules that I'm not reporting here. So what do we have here? We have fake enzyme. Fake enzyme that does a good job in sensing. Okay? So that's my first fake material so far. Alright, let's talk about templated grafted polymer brushes. Okay? And polyelectrolyte multi-layer. So in our lab, we do a lot of polymer grafting. We also do a lot of things related to layer by layer of polyelectrolytes, and in this case, polyelectrolyte macro initiators. Okay, so I know in Takahara-sensei's lab, a lot of this is quite common, and you can identify with this work or some of our work. But more recently, we were interested in Lotus Leaf. Okay, as a lot of you know, this has been cited for superhydrophobic effect. Now, this is really due to several things, but one of the things that the Lotus Leaf has is the hierarchical roughness and topology. And all this can be traced to what we call the Cassie-Baxter phenomenon, which is trapped air that prevents the formation of a line or continuous line tension of wetting. So the question is, can we make a fake Lotus Leaf even better? So to do that, what we did is we copied the features of the Lotus Leaf using polydimethyl siloxane, a very common material used for stamping. Okay, so we copied the Lotus Leaf pattern on a PDMS mold, and then this PDMS mold we imprinted it on a cellulose acetate film. We then did layer by layer of a polyelectrolyte macro initiator for ATRP. And then we grew a well-known LCST polymer, poly-9PAM, that of course has a transition of 37 degrees C. And then this is how the morphology looked like. So the original Lotus Leaf, the fake Lotus Leaf, and then after growing the polymer brushes, and you can see here some of the peninsular or corpuscle type of structures compared to the original. Okay. Of course, a very important tool here is actually IR imaging. In infrared imaging, which I'll use in several examples today, we can determine the chemical composition, the morphology, as well of an optical diffraction-limited image, and then obtain chemical information. So this intensity allowed us at various frequencies to confirm the presence of cellulose acetate, poly-9PAM, okay, and PDMS, okay, based on the frequency. Now, how did this perform? Well, first of all, if we have a flat surface without a Lotus Leaf replica, okay, this is the behavior. The NIPAM has an LCST of 37 degrees C. So below 37 at 25, it's wetting, hydrophilic, not the best. But then heating it up to 40 degrees C converts it to hydrophobic, which you see by the increase in contact angle from 62 to 90. Now the question is, how did the Lotus Leaf replica work? Well, the Lotus Leaf replica, when we cool it at 25 degrees C, completely wetted the surface, 0 degrees C contact angle. And then when we heat it up with a difference of about 50 degrees C, 25 to 40, you have a dramatic change from 0 to 153, or what we call super hydrophobic. And not only this, one time, this can be switched back and forth, back and forth, back and forth, simply by changing the temperature 50 degrees C. So this is basically a Lotus Leaf replica that was improved upon by converting it into a stimuli-responsive polymer. Okay? So this is your second fake material. In fact, to carry on the work with layer by layer films, we did something called molecular, or rather macroscopic or microscopic folding mechanisms. So in Japan, of course, everybody has to learn origami, right? You have to fold, you have to make different shapes, and then come up with a crane. Okay, we're not quite there yet. So what we wanted to do is, can we do this in a microparticle? Can we fold a cylinder or a square or a cross into a cube or a pattern? Okay, and in order to do that, we need to lift the particle from the host substrate, and then we have to have a mechanical dual property, a hard and a soft layer that will bend with appropriate stimuli. Okay, so to do that, we actually embarked on this procedure where we made a pattern by lithography or reactive ion etching, and then we took this pattern and then we added layer by layer by layer of polyelectrolyte, and then we evaporated aluminum on top of it. Now, evaporating aluminum gives us the hard layer. The soft layer would be your polyelectrolyte layer by layer, and then this was put on top of a sacrificial polyvinyl alcohol layer, such that when we put it in water, it will dissolve the PBOH and then lift up the particle. So in other words, what we wanted to do is achieve particles that can be observed to fold under microscopic conditions. So here you can see the fidelity of the pattern. We can make very nice edge pattern, edges that are high fidelity. In this case, a cross. Again, the composition was monitored by IR. The structure was observed by SEM and AFM. And these are the different objects we printed, or rather we lithographically patterned. So we have crosses here, and you put them in water, they start moving. And then the independent ones, they start folding. Okay? So we observe this folding mechanism on this process. Or if we take a cylinder and then we lift it from water, they start folding into tubes. So we get these tubes. Or this tuning fork-like structure with various lengths, we can see that the longer arm starts folding faster than the shorter arm. Okay? So this is not exactly origami yet, but we believe we're getting there. Okay? So this is your fake origami. Third. Alright. Electronanopatterning and conjugated polymer precursors and macroinitiators. So one of the things we developed very early in my group is the use of electropolymerized monomers attached to a polymeric backbone. Now we do this because a polymeric backbone, like here, can drive the solubility or even the electronic property. But the presence of these electropolymerizable monomers attached to a polymer means that at one point they can form a ladder polymer, which we don't observe or rarely observe. But more commonly, they like to cross-link as a film. Now this is very important because cross-linking renders this a thermoset material, meaning it fixes on the surface. It does not dissolve, it does not go away. Okay? This is a cross-linking process. Because of this, we can make very stable and efficient devices. So for example, very early on, with LED material based on polyfluorine, we can change the turn-on voltage and the electronic properties by tuning the properties of this oxidized polymer and then seeing how it changes the function with respect to ITO. Now ITO is a very important substrate, as most of you know or have used, because it's a transparent electrode. But when you get an ITO, it looks like this. It's ugly. Okay, it's rough. And in order to use it, you sometimes have to clean it. You need to, for example, put a self-assembled monolayer. In our case, we actually grew polymer brushes. So we grew the polymer brush on ITO, and after growing polyvinyl carbazole, for example, we get this smooth, nice film. Now, not only is it smooth, planarized, but it also improves the whole transport layer properties in an LED material, such that after we have added it and cross-linked it on a surface, we can actually get very efficient devices, both LED and all photovoltaic devices. Okay, so let me skip that part showing the performance, but rather focus on a specific aspect of patterning. So this was a polyfluorine that we synthesized, having carbazole units that like to cross-link because of the carbazole group. And then what we did is we patterned it on a substrate with 25 micron dot structure. So these are 25 micron electrodes. And notice here we get very nice contrast of the blue emitting material, because electrochemically we can site deposit on this dot structure in the presence of this carbazole. Without this carbazole, we get a mess. We get a bad film. Okay? But by utilizing this precursor approach, we can do patterning. So this is our first foray in what we call micro-patterning of electropolymerizable precursor polymers. Now, similarly to my stay in Japan, I actually stayed in Singapore, there for about 1 month. And on my first stay in Singapore, for 3 weeks, I enjoyed, going to Orchard Road, shopping, Takashimaya, Sentosa, whatever. Last week, I had no results to show. Okay, nothing. I did not do anything in the lab with Suresh, believe it or not, okay? So I told the student from Suresh, I'm sorry, I had no results. I enjoyed myself in Singapore too much. But one thing I like to do with your student, I like to spin coat polyvinyl carbazole on gold. And then we want to test an AFM tip that's conducting. And then we move that tip on the PBK, and let's hope we can see a pattern, okay? So we actually did a quick and dirty experiment, and lo and behold, we get patterns about sub 100 nanometer line, all by simply moving the AFM tip on conducting AFM experiment. So with this, we were able to build different structures, memory devices, different types of layer-by-layer films. And in fact, it was very fortunate when I was in Singapore, and always in Singapore you have a weather like this, very hot, very humid. The experiment worked. The reason the experiment worked, we found out later, is that high humidity produces this wetting electrochemical bridge between the tip and the substrate. In fact, we verified the presence of this high humidity environment by doing the same experiment in vacuum. We did it in vacuum, no result. We reduced the humidity up to 5%, no result. But when we do it in room temperature environment, everything worked very well. So it's the simplest method to nanopatterning, electronanopatterning. Okay? So we got many papers, and in fact, one of the easier papers to work was on a layer-by-layer polycarbazole precursor. So if you know layer by layer, of course, all you need is you can take a negatively charged polyelectrolyte, a positively charged polyelectrolyte. You pair them up layer by layer in a beaker experiment, and then, in this case, these are polymers where we actually have carbazole units. that like to react and cross-link. Okay, so we built that film and we increased the number of layers and we cross-linked them using electrochemistry, and it worked very well. This was a partnership between Cheng-Yu Wang, who did most of the synthesis, and then Guoqian, who did most of the patterning and the electrochemistry. Okay, so I asked Guoqian to try to do different patterns. So he did lines, he did squares, he did different types of logic circuit-like structures. And then one night, I was about to go home and I was looking at his work. What are you doing? He showed me a heart. Okay, I asked him, you know, why are you making a heart in the lab? We're supposed to do serious things here. Okay, and then he told me, I want to make a heart. Period. Okay, and then I noticed for the next 3 weeks, he and Cheng-Yu, they like to work late at night. Okay, so after 3 weeks, they came to me and they said they want to get married. Okay, so they got married. They published the paper. In fact, they got a cover page of macromolecules out of this work. Okay, so I'm just letting you know there's also love in macromolecules. Okay? You can have love. So anyway, to continue some of that work, we took this type of chemistry. We designed what we call an electropolymerizable macroinitiator. So here you have a conducting polymer that is formed by the reaction of this tertiopine, but at the same time it contains a raft chain transfer agent for raft polymerization. So we would pattern this or deposit this conducting polymer. We can grow a polymer brush, in this case PMMA, and then a block with polystyrene. So you can easily make these electrografted or electropolymerizable macroinitiators. So we did that, for example, with a simple pattern, PEM pattern ITO electrode, as shown here. So we would electrodeposit the chain transfer agent for raft. We would grow the polymer brush by raft, and since the middle part is still ITO, we can then add another initiator for ATRP, okay, in the middle, and then grow another polymer brush by ATRP. So in essence, we can make 2 types of polymer brushes within these patterns. And to prove that, okay, here we have an AFM of polystyrene. But then after the fixation of the ATRP initiator, we will grow poly-NiPAM right here. So this original pattern was translated into this pattern. Okay. Now you will not know if it was polystyrene or poly-NiPAM unless I tell you, right? Just by looking at this AFM, you will tell me, what is this? You don't know. We don't know. So that we did, to prove the point, we utilized IR imaging to make sure we have a chemical map of the polystyrene and poly-NiPAM distinguishable. So for example, the green region here represents that of polystyrene. No carbonyl stretch, no NH stretch, but a nice CH stretch around 3000. On the other hand, we know that the blue or greenish blue is poly-NiPAM because we have a nice carbonyl stretch, a nice NaH stretch, but a lower CH stretch for the polymer NiPAM backbone. Now this again is to emphasize you that when you do this type of chemistry at interfaces, tools, tools, tools. Okay, surface analytical tools is very, very important because just one experiment proves your point. Okay, so in a number of configurations, of course, you have to employ spectroscopic, microscopic, acoustic, chemical analytical tools to do the story or complete the story. Now, I believe I still have time. Let's try for this 4th one and maybe even finish with the 5th one. So in colloidal nanosphere lithography, how do we prepare things in terms of colloidal particles? Well, a colloid particle is essentially paint binder particles that are made by motion polymerization. If you order them as a flat film, meaning one layer of particles, they actually pack very well. And they pack by a hexagonally packed structure because they're perfect spheres. Now what happens is this perfect spheres essentially contains surfaces or or interstitial spaces that is amenable actually for electrochemistry. So what we will do is we will electropolymerize on these interstitial spaces such that we have an array or a pattern of conducting polymer underneath these colloidal particles, and then we can simply remove or digest the particles, and then you will be left with a pattern. Okay, so we templated these colors, and the result is as follows. We can make a beehive-like structure, a half-dome-like structure, or a full dome structure. In fact, it is so interesting because this full dome structure, we can harvest them as particles, okay? Simply by delaminating them from the surface. So in fact, this may be another way to make colloidal particles based on non-lithographic methods. At any rate, what's interesting is we can electropolymerize conducting polymers underneath. And so this is a pattern of polycarbazole that was electropolymerized. And then after removal of the colloid particle, you have actually a conducting polymer array on an ITO surface. But then the middle part here is still electrode, ITO or gold, okay? So that middle part, we can then graft an ATRP initiator and then grow a polymer brush. So this is basically a conducting polymer with polymer brushes in the middle. To do another analysis, we use conducting AFM to show that the green versus the blue region represents a more conducting IV junction versus a insulating or non-conducting function. Okay? And this colloidal templating can in fact be extended to the previous work. So we can make macro initiators for ATRP, for RAP, for metathesis, and then after we pattern this polymer macro initiators, we can then grow a polymer brush on top of it. So as you can see here, the patterned macro initiator conducting polymers, and then after growing a polymer brush, you can see these thickened lines. Basically, the polymer brush grew on top of the conducting polymer. And then we did that on all three of them. So these are, again, examples for metathesis and ATRP. Or the middle part, we can grow another polymer brush, and then we can have a brush on a brush. So brush on top of the conducting polymer, and then another brush. So we have polystyrene, poly-NIPAM, or polystyrene PMMA that are distributed bicontinuously, not bicontinuously, but arrayed as a bifunctionality on a surface. Okay? And we've actually used it for sensing. More recently, we have used it for patterning viruses. So this is a cowpea mosaic virus that was patterned on a colloidal array. And as you can see here, very nice pattern. They like to congregate, aggregate near the holes. And actually we can lift them up from the surface so you can get freestanding film of viruses on colloidal templates. Okay, so I think we have room still for the last example, and then we'll finish, okay? And then we'll leave this time for questions. So you guys can wake up now. So here is the polyelectrolyte. This is the polymer multi-layer that is different from the polyelectrolyte layer by layer that we've shown. Now, I'm a part of the center called CLIPS, and we can prepare multi-layer films by co-extrusion. What we do here, instead of the layer by layer of polyelectrolytes, we actually form the nanostructured layers by extrusion. So if I take polymer A, polystyrene, polymer B, PMMA, and then I melt them. So as they're melting, I'm pushing them, okay? And then as I push them, they form films. And then as they form films, they lay on top of each other, okay? That bilayer is basically A and B polymer, okay? And then I push them further, and then I cut them in the middle. So as I cut them in the middle, they separate into two tracks. And then I rejoin them by putting them on top of each other. How many layers do I have formed so far? 4. Next, I push them forward, I cut in the middle like this, and then I put them on top of each other again. How many layers have I formed? 8. Keep on doing this, doing this, doing this 160 times. In fact, I ended up with 4,000 layers. Okay, 4,000 layers would represent 10 nanometers of PS and PMMA on top of each other. That is almost the limit of the distinguishing features of a high interaction differential parameter. Essentially means that we can build a lot of chemistry, lots of interesting chemistry on these multi-layer films. We can, for example, build a gas hose system for drug delivery. We can do patterning by polymer brushes on top of this film. We can do microparticle fabrication by chopping or cutting this film so that you can see here it still reveals the layering order on each of these particles. Or we have done, or my colleagues rather have done some membrane type of work based on fibers generated using this process. So first project, we have done, for example, nanosheets by basically making layers of polystyrene and polyethylene oxide or polycaprolactone and polyethylene oxide. These layers was put on water. What happens? PEO or polyethylene oxide is dissolved by water. So as the water dissolves the PEO, the sheets of polycaprolactone start separating. That's why we get these nanosheets. These nanosheets were generated from the separation of those layers by dissolving the PEO. And we have actually used them for drug delivery and control release type of studies. Here, we grafted this benzophenone ATRP macroinitiator into patterns. We grew the polymer brush, and we found that we can distinguish the polymer brush behavior with the wetting as well as the functionality on the surface. Or we can prepare on top of those patterns a micro-imprinted feature, either as lines or dot structures that can have photonic features. In fact, those layers are essentially photonic band gap structures. So this type of layering here, if you control the refractive index and the thickness, essentially controls the wavelength. Okay, and in fact, you can insert nanoparticles here. This becomes metamaterials. That's another story. But then, what's interesting is that we can take these layers and then start chopping them or start doing lithography. When you do lithography, in this case, you can produce cubic particles. You cannot access this by colloidal methods, but cubic particles based on lithographic patterning and harvesting. So we make these particles basically by chopping or patterning these multi-layer structures. And so these films here, as you see, are converted to particles. The layer structures are still maintained. Inside those particles, we can control the depth, the shape, the height. We can make various types of sizes, but the main thing is inside those particles, we have controlled layer structures. So that means these particles can be used to produce band gap structures, metastable or metamaterials, or it can be used for drug delivery, it can be used for making different types of colloidal systems by lithographic methods versus using emulsions. So believe it or not, I'm ready to conclude. Some perspectives for the future. Molecular, macromolecular, and particularly templating and design means more chemistry for you. Okay, so chemistry synthesis is powerful for materials. Secondly, in a bottom-up approach, you converge function from nanoscopic to macroscopic, or you converge design. So you take nature, copy it, and then go from top to bottom. For patterning and nanoparticling strategies, as I've shown you, is quite a hierarchy. You go from nanoscopic to macroscopic. Another is, I hope I've emphasized to you the importance of surface-sensitive analytical tools, whether it's SPR or IR imaging, and looking at mimicking nature or design. In fact, one of the best ways to copy nature is 3D printing. Okay, you can digitize an SEM or TEM image and then reproduce it. And then lastly, I've shown you high throughput fabrication of particles in some application. So I hope this seminar not only informed you about science, but equip you with some principles or maybe some inspiration on innovation. So with that, I'd like to close the talk, and I'd be happy to answer any questions you may have.